Welcome you all to this cryo-EM course. Last class I discussed with you how we can freeze our cryo sample using VitroBot, and similarly we can use other instrument also to freeze our sample. So sometime we are using the manual plunger also, that where the manual plunger will help us to freeze the sample and manually we have to blot the sample. Here you have to pay attention one important part, that when we discuss these things, that for the negative staining sample preparation generally 0.1 mg per ml sample is good enough for the negative stain, but for the cryo we need at least 1 mg to 2 mg per ml sample. Why there is a so much high concentration samples are required? Because if you consider that what we are doing, we have a grid, the circular grid, and then we are adding a small amount sample on top of this grid, and then that grid is somewhere here and we are using 2 blot paper and trying to blot that sample. When you are trying to blot the sample, because of this kind of blotting method, most of the sample will go away. So generally for the negative staining, if this is the grid, we are adding a small amount sample and from the side we are using a filter paper and we are trying to blot that sample. But for the cryo grid, so grid is blotted like that, and most of the time lot of sample will blotted away by this blot paper. That is one of the reason we want to use a higher concentration of the sample, and also in this particular grid we have a hole only where the sample will stay inside that liquid solution at different orientation. But in a continuous carbon, for negative staining room temperature sample preparation, there is a carbon layer and your sample will stay and attached that carbon. But here there is a hole in a cryo-EM grid, sample will stay, and then we are using blot paper to blot that. So that is another reason that there will be many sample will be blotted away from that holy carbon grid. That is one of the reason most of the time for the cryo sample preparation we need much higher concentration than normal room temperature temp. Now if you remember the last class, I discussed about how to image our sample, as well as we focused on that okay, there is a raw image, and then from this raw image we have individual protein molecules. From that individual protein molecules we are calculating a 2D averages. So if you look at my slide, you can see that okay, here we have that sample here, that liposome, and here you can see the liposome and the individual protein molecules. Again the same slide I am showing here. Now if you look at here, this is an enlarged view of this same liposome where you can see proteins are attached with that liposome, but here you cannot identify the shape of the protein very well except this top view. In this top view you can see this heptameric protein, but from the side view you cannot see this heptameric protein anymore. So now if you calculate the 2D averages, you can see a very nice shape of this sample. Now if you go take those 2D averages, if you back project them, finally you will get the 3D structure. Now the first question it is coming, how many particles, or this we are calling a single particle. So this is one of the particle, this is another particle. So we are just adding single protein molecules together, and then we are calculating a 2D averages. Now if I ask that how many protein sample or single protein molecules or particles are required to get this kind of 2D averages and this kind of 3D structure, then what is required there? How many images are required, or how many protein samples are required here? So that answer that okay, so it may be 5, 10, 20, 30 particles is good enough, maybe or maybe not, that we don't know. So here I am showing you one slide where in between there is some object is there, and now there is a camera. This thing is taken from particular this image, and here you can see that okay, there is some object is there and then there is a camera. And if I just ask you that okay, what kind of object is here inside that. So if you look at this particular image, it will look like that you have a hand in between here, you have a hand, and that projection you are getting here. Okay. Now next step, I am going to remove this and we will look at this object. Now you can see this is really not a hand. Basically this is a rabbit in a dancing condition and it is looking like a hand. So what we are looking here, we have a 3D object and then there is a electron beams are going through and then we are getting a 2D images. From these 2D images we are trying to project our 3D object. So there is a high chance we will end up with a wrong structure if we have only one image. What happened at the beginning, because when I block this one, we don't know, we are looking at this particular image and from that particular image we are trying to predict what kind of 3D structure is inside. So definitely one particular projection is not good enough to get a 3D reconstruction. Why? Because it has to satisfy all the angle and each and every direction. So it can satisfy everything, all the Euler angle. So here that is the reason we need different orientation of these protein molecules. If there is a very biased orientation, then probably we will not get any 3D structure. So if you just consider in this particular sample, so here we have an object and object is this. So if we have an object, there is a two major things we can expect. That 2D image, if we are expecting, we will expect this kind of 2D image, or if we just rotate this one 90 degree rotation, what we will get? We will get circle, or if there is a 45-degree rotated angle, what we will get? We will get some kind of tilted view of this one. So that will go in all direction. Now when we are trying to do an imaging, so what we will get, either in this 2D, either we should get all these three projection, or some cases what we will get. So in this particular case we may get all this projection. Okay, we will get all of this. So if we are getting all of this, means it is well distributed and different orientation we can find out. So we can add all of them together and get, we can back project them to get a 3D structure. But in some cases, if we have an image and we are getting only, so same object we are using the same object and we are getting only this kind of shape. That means it is a very preferred orientation. Even if we are trying to freeze cryo sample, their preferred orientation, and we are getting mostly the top view of this sample. If this is the top view and this is the side view of the sample, we are getting only the one view. And the other condition, if you just consider that, we are getting only this kind of view. This is also a very biased view because we don't have all the views here. So it is the side view it is showing. So from this kind of pattern we will end up with a wrong 3D structure, because if you try to back project all of them, we will just get one circular disc. We are not trying to fulfill all the angle of this 3D structure. So one condition, that if we have only one particular image, or if we have one particular orientation of this 3D object, and if we have this kind of image, we cannot get any 3D structure from those images. So that is one of the reason we need very high number of data set for any 3D reconstruction, and it should satisfy all the angles. So here when we are talking about the single particle analysis, we are targeting the individual molecules or individual protein molecules. When we are thinking about tomography, what we are doing, if this is our sample, we are tilting the stage. So if we look at this sample in particular, that okay, we have a sample here, and then we tilt the stage physically, we are changing the physical position of the grid, and we are keeping it at same axis, and then we are collecting the tilt images, and we will tilt the stage almost 60° plus and minus 60°, and we will add all of this data together to get a 3D volume out of that. So this is called the tomography. So there is a two way, that one we can use the single particles of this protein where you have a different orientation, and then we can calculate a 3D structure. The other way it is that you will collect a tilt series at cryo condition, and then add them together and calculate a 3D volume. So if there are any tilt series missing, it is going to affect our 3D reconstruction. Now let's discuss about that. Okay, we collected the images, but when you are collecting the images, I already showed you at different magnification. Sometimes it is a very whole size is very small, sometimes the whole sizes are very big, very large, and then different magnification. So first, whenever we have a grid, we will insert that grid inside the microscope, and then we have to look at that grid and we have to figure it out which area is good for imaging. Let us discuss about that. So here I am showing you a same TEM grid, a cryo-EM grid, and this is a frozen cryo-EM grid, and if you look at this frozen cryo-EM grid, we insert, we can see that individual square, and you know, if you are looking at this particular grid in TEM at room temperature, probably you can see each and every individual square, there will be no problem. But whenever you are adding sample, then you are blotting that sample, then you are quickly plunged into liquid ethane. Then if your blotting is not appropriate, or in some area of this grid absorbs more water, and if it is not blotted properly, and if it is quickly plunged into liquid ethane, some area will get a very thick ice, some area you will get a different types of moderate ice, some area if blotted very strongly, most of the water will go away, and that time you will see only the empty holes. So all these possibilities are there. That is one of the reason it is very important to fix the blotting parameter. Blotting parameter means blot time. So blotting parameters means that, okay, so there are couple of things. So first thing is that blot time, that how long we want to blot our sample. So generally 4 second to 5 second or 3 to 5 seconds. Sometime in some cases people are using 7 seconds or 8 seconds also. Then blot force. So blot force, there are some parameters are there. So blot force we also have to consider that how much blot force do you want, and those parameters we have to optimize when you will freeze our sample. So there is no fixed value that we can tell that, okay, so particular one paper they use at 3 seconds blot or 5 seconds blot. That same parameter it is going to work for the other equipment, that is not possible. So maybe the sample is same sample, someone use it 3 seconds. When you are changing the facility and going to the other facility, you are using a different types of grid. Based on their facility, you have to set those parameters, that how many seconds you want to blot, what will be the blot force, and which blot force we are getting good eyes, that you have to optimize based on that equipment. So if something is mentioned in the literature that okay, 5-second blot is good enough for that protein, same blot parameter it may not work in your facility. So that you have to pay attention to those things, or same blot force may not work. Now when we have this grid, the next we want to image. I already mentioned that okay, so in this particular imaging, when we are using the blot force or the blot time, sometime it will absorb the buffer or solution properly and you will get a very thin ice. Some cases it will not blot properly and you will get very thick ice. Now if you look at this particular square, we are expecting to see all these squares properly at enlarged view. So here we are using 115x magnification, and this enlarged view, if you look at in this particular grid, we can see there is a huge area is completely black. That means in this particular area there is some square, this area also there are some square, but these are so thick ice we cannot see individual squares anymore. So those are all basically blocked because very thick ice and electron beam cannot go through this area. On the other hand, if you look at here in this particular squares, the square size is very small. Why? Because this is also very thick ice area, and that is the reason majority of these squares is blocked by the thick ice. Now if you look at here, this is one of the good square where you can see most of the square area. So if you just consider this particular square area and the nearby, it also have the same square area, but due to this thick ice this entire area is looking black. So from this particular grid what we can conclude that okay, this is a very thick area, this will be completely useless because electron beam cannot go through this ice. Here you have a comparatively thinner ice where at enlarged view you may see a very nice distribution of the ice. That will go and check those grids in the later stage. Now if you pay attention to this particular square, there is some at the center position, you can see there are some broken area in between. So this may be due to the handling issue. I will show you when carbon layer will damaged how those grids will look like. And in this particular case you can see a black patch at the center. This black patch is the center, that means there is, when there is a blotting, the center area there are some buffer droplets are there, it didn't blot properly, and that is forming a very thick ice at the center of the square. Sometime because of the glow discharge parameter of it is not glow discharging the grid properly, you can see this kind of problem. Now if we go to the next square, in this next square you can see it here. So if we look at the next square, better to erase. Now in this next square we can see, here you can see this is a proper square area, but if you look at, there are couple of squares, this particular square or this particular square or this particular square, there is a nothing is inside, because if there is a ice or carbon layers are there, so it will form some kind of gray color, something like this one, something like this one. But in this particular case you can see some black patches are there and the centered area is completely white. Here also you can see part of this area is damaged or there is a crack in between here. So this is there is a crack inside here also. So this is basically handling issue. So those carbon layers are damaged, or maybe the grid is glow discharged for very long time, which damage those carbon layers also. So if you glow discharge grid for a very long time, that may damage the outer layer of the grid. Now the next one. So now we focused on this particular area. In this particular area we can see it that okay, this is very nice square where overall squares, most of the squares area are clearly visible. Some squares are little bit smaller size. If you compare this square with particular this square or this square with this square, definitely here the square area is much bigger than this one, because this area maybe there are some extra buffer is deposited which is making a very thick ice. So that is the reason electron beam cannot go through and the overall squares areas are small. But in this particular grid we can tell most of the squares are very good. This kind of squares is suitable for cryo-imaging. Now there is another example that is also very important example, that here you can see this is a square that I was discussing at the beginning, that okay, there is a black patch on inside this every square. And if you look at here in all these squares, so you can see there is a very small white dots are there. Those small dots are basically that hole, that is I am talking about 2 micrometer or 1.2 micrometer or 3 micrometer diameter hole size. So we are looking at those hole size, but the center area there is a black patch. Those black patch basically it didn't blot those buffer properly, and this when we plunged it, all this, if it is not blotted properly, the liquid will stay there, and when you will plunge, everything will be deposited in that particular square and it will make a black patch inside that square. And that basically we are looking here, this is basically thick ice and electron beam cannot pass through this thick ice, and that is why it is appearing as black. And these are the area where we can see the hole also. So whenever we will insert a grid inside the microscope at very low mag, will screen this entire grid at different position, and we will try to figure it out where we have the better square, and based on that we can plan next. That okay, in this particular grid we I already showed you this area, there is a lot of broken and thick ice area. Then this particular area we have a lot of broken squares, so this particular area is also not good. Now I have another area where I am imaging this area is good. So from after screening this entire grid we can decide okay, this may be the best area where we can go for imaging. Now in this particular case, this is the area where we can see at least some individual square. One square is this one square is this one. It is looking a good square, we may image. So here I just want to show you, this is the grid we are not going to use for imaging, just we want to show you that okay, at different magnification how these grids look like. If you come here, you can see it that we are targeting particular one square, as I mentioned that here there is a blue star is here, we are targeting either this square or this square. When we will go from 150x magnification to next magnification, that is called 380x magnification. So 380x magnification, you can see little bit enlarged view of this particular square. In this enlarged view you can see this is the square boundary and those are the individual holes that we are talking about, that where our samples are. So here you can see there is a one blue dot is here, that is we are targeting one of these hole for the imaging. And if you look at this particular square, what you can see it here, that okay, we are targeting one of the hole and there is another star nearby area. So here if we just from 380x magnification, if we go to the next magnification, that is 4300 is 300x magnification, where you can see the proper hole size. This is our proper hole size. This is our camera sensor. This blue circle is the beam diameter of our microscope. Now our camera can image only this particular area, but just after this square there is a carbon area. This is the carbon area. Then what we are doing here at the carbon area, because there is another same beam diameter is there, where we have that focus area. So here what we are doing, we are focusing on the carbon area, and then we are coming back and imaging the sample inside the hole. And when you are collecting that data, it will be a very high magnification. It is 36,000x magnification, or it may go 45x magnification, or it may go 55x magnification. Now this particular stage, if you look at this particular stage, this is the stage where this particular stage, what we are trying to do here, if this is one of the hole and this is the another hole, we are targeting this particular area and we are doing the focusing here. So we are trying to keep the focus in between all the hole. So if there is a two holes are there, here we have a two holes, we are targeting to do focus somewhere here. So this focus beam diameter should not touch any hole, and then we are imaging in this particular area. If focus beam diameter is very big, and if it exposed all the holes, it is going to damage all the eyes. So we have to maintain a proper hole diameter here, beam diameter here, and that beam diameter we have to position in such a way it should not expose, or that beam diameter should not touch any other holes when we are going to do the imaging. One more important part, we have hole here, we are focusing somewhere here and we are imaging somewhere here. We are trying to maintain some distance, and also focus we are doing on the carbon area. This is the carbon area, if we recall properly, and this is basically hole where we want to do our images. Now if you look at the carbon area, why we have to do the focusing on the carbon area? We have to do the focusing on the carbon area. What is wrong if we just do the focusing somewhere here and then image immediately there? So whenever you will do the focusing, you need some time to do the focus, and here you have the amorphous ice only, and during your focus the amorphous ice electron has lot of energy, and that is going to damage your amorphous ice, and your ice will start melting. There will be a thermal drift, your sample will be beam damaged, because electron has lot of energy and it can damage the biological science sample, that we already discussed. So that is one of the reason wherever we are imaging, if we are imaging in this particular area, we cannot do focusing here only. So that is one of the reason we are targeting, this is the imaging area. So that is the reason we moved somewhere else, do the focusing on the carbon area, and then we come back and image here, and this entire process we can do it automatically nowadays. So always remember that whenever we will do the imaging, we image inside the hole, and focus on carbon area, and we also have to keep some distance. This beam diameter should not touch each other, and this beam diameter should not touch the other holes also in the nearby area. So whenever we will focus, this focus beam diameter should not see other holes. So we have to position this focus in such a way it should not damage the nearby hole. So we have to control the beam diameter also properly, and also we cannot focus in same position because it is going to damage our sample completely. Now I will show you some of that enlarged view of those holes where you can see different kind of ice pattern, and we will discuss about this more in the later slide. Here you can see so here in this slide you can see it that okay, these are the individual holes. There are some black patches. So whenever we will focus somewhere in this particular region in between those holes. So here you can see one of the hole where these squares are completely broken. This kind of square we should not use it for imaging because it will be very difficult to adjust your Z. And here you can see some kind of contamination or black patches or patterns are there. This may be contamination is coming from the liquid nitrogen or liquid ethane, or some kind of ice contamination is there. This is again some kind of black ice contamination pattern. Those are the broken square. So whenever there will be a broken square, it will be better to avoid those broken square because you cannot adjust your eccentric height. So here you can see individual holes where there is some black spots are there. These are basically ice contamination. And here there are couple of more squares are there where maybe due to the temperature increase or some other parameter changes or because of the bad handling, you can see different kind of ice pattern. We will discuss these things more in the next class. That time I will show you the good images and bad images also, and thank you all for your attention.